All
Hello,
right.
welcome to the next CIR talk. Today we have Professor Andrew Yates from University of Amsterdam. He's an assistant professor. He's been working on neural IR. He has co-authored a kind of quite a popular book in this area called Pre-trained Transformers for Text Ranking, BERT and Beyond. Before joining University of Amsterdam, he was a postdoc and senior researcher at Max Planck Institute for Informatics, and he received his PhD from Georgetown University. So without further ado, we're so excited to hear about flexible representations with learned sparse retrieval.
Thanks, Ahmed. Yeah, so this is a totally new talk. It's been a busy week, a lot of fun making slides over the past week, so I'm excited to give it. Just a very quick about me slide. It doesn't seem to be moving. Okay, I'll click this. As Ahmed said, I tend to work on neural methods for information retrieval. Really, I'm interested in these content-based methods. So I've been at the intersection of IR and NLP for most of my career. I'm in the IR lab at the University of Amsterdam. I have my own little subgroup here. So you see pictures of either current group members, recent group members, or collaborators on the work I'm going to talk. But we focus on these content-based methods for improving ranking through better language understanding, essentially. So what I want to talk about today, move this out of the way, is these flexible representations for learned sparse retrieval. And to set the stage for that, I want to talk a little bit about how large language models work and why they're so convenient and easy to use, or one of the many reasons. So natural language text is just a really flexible medium for input and output. So you see here the Claude LLM. I can ask it to write a short sentence about Amherst. It'll give me a short sentence, right? Amherst, vibrant college town, known for its rich academic culture and scenic New England charm, etc. So there's nothing groundbreaking here. And we're quite familiar with these models. We know they create natural language text. That's what they do. They're generative models. One property that I think we're all aware of is that these models, because they output this natural language text, they kind of have this unified representation space. So I don't have to take a dense vector or some latent representation from Claude and teach ChatGPT how to use it and then plug that latent representation into ChatGPT. I can just give it some English text. Despite the fact that these models were trained entirely separately, as far as I know, they know nothing about each other. They're totally separate models. So I can take that description I got from one of them and ask it to make it much more dramatic. I get something a little ridiculous out. Amherst is a lively epicenter of intellect and inspiration, where the pulse of academia meets the timeless beauty of New England's landscapes, creating a town that feels both electrifying and steeped in history. So I think this is, of course, not surprising, but it's worth thinking about why this works, which is because we have the shared representation space. We don't have to train the models together. We can simply take the output from one and plug it into the other. And of course, as you know, we can go further with this. So for example, I can give that text to Gemini and ask it to judge on a scale of 1 to 5 how over the top that description is. It's very conservative, or maybe just not as dry as me, and it rates it at 3. I think this is at least a 3.5, probably even a 4. But whatever, the point is it understands the text, it understands that this is over the top in some way, and it can produce some numeric, it can produce the rating of that, despite never seeing this text or these models before. And of course, we can do that in more complex pipelines, I think, as everyone is well aware. So maybe we have models that perform different functions. Here we have a describer model. So it looks at the simulated world. This is not my work, just an example, and tells the builder model what to manipulate in that world to achieve some desired outcome. So it asks to move some colored squares around so that they're in a different pattern. The builder understands that natural language output, it moves the squares around, and now we have a new state of the world. We can, of course, imagine much more complicated pipelines like this. Again, not my work, just an example from an CIIR paper. Here we have a complex problem about manufacturing planning. There's some sort of sizing problem. And so, we have all these various roles that LLMs can fulfill. We have this terminology interpreter that describes what the term backlogging and input means. We have some modeling expert that defines variables. We have some programmer that outputs a Python script. We have some way to critique and refine this output and iteratively mess with it until we get something that works. And then at the end, we get an answer out. So again, the point I want to make here is that these are all totally separate language models. Maybe it's the same underlying checkpoint, maybe not, but they can communicate with each other through language. We don't have to worry that the terminology interpreter outputs a dense vector that can be used or is compatible with some dense vector from the modeling expert or the programmer or whatever. They're not operating in some latent space. They're all trained to produce English. And to the degree they can take English as input and produce English as output, they can all be put together in Lego-like ways and work together without having necessarily seen each other before. So that was a bit of a sidetrack. This is about large language models. What I really want to talk about is how we can get this sort of flexibility for representations, but in the context of ranking. So I don't think I need to spend much time on this slide. Everyone here is familiar with ranking. Just to make it crystal clear, we have some sort of query like UMass Amherst. We have a document collection. We have a ranking model that ranks documents in that collection with respect to the query. We can measure the how well this ranking model did with some metric like precision at 3. In this talk, I'm going to be focusing on the ranking model and the types of representations it uses to do its ranking. In particular, I'm interested in content-based ranking. So I'm interested in comparing the language of the query to the language in the documents and determining what's a good match based on that. Of course, there are many other ways or complementary ways to do ranking. There's this learning from interactions that you see in learning to rank and so on. I'm focusing today on these content-based models. So what would that type of flexible representation look like in the setting of ranking? For comparison, let's think of dense retrieval. So in dense retrieval, we take that query. We have some sort of dense encoder. This encoder outputs what is sometimes called a dense representation. Dense here just refers to the fact that all the values are used in quotes. We expect to have very few, if any, non-zero values. They're all non-zero. And we expect these to be some sort of latent entangled dimensions. So you see here, UMass Amherst becomes a vector of size 10768, and we can't really interpret the dimensions. We see some are bigger, some are smaller, some are around 0, some are negative, and so on. But we have this latent vector to deal with. Now, learn sparse retrieval, which is what I'm going to talk about today, is a different way to approach this. Where we have a larger vector, we expect it to be sparse. We expect most of the dimensions to be 0 values. And here I'm showing some of the values that aren't 0. And we expect this to be grounded in language, or it's often grounded in language. I'll talk a little bit about prior work later where it's not. So you can think of something like TF-IDF, or maybe an impact score from BM25, and it can follow the same rules, right? So this score for UMass of 1.9, here it's coming from this sparse encoder, which in this example is some sort of neural model, probably a transformer. But we could, calculate the TF-IDF for UMass and fit everything into the same framework. The point here, though, is within this neural framework, within this world of transformers and transformer-produced representations, we can create these representations that are grounded in language, like the LLM output. So we can make sense of them, we can combine them, we can refine them, we can debug our models. And we can also get most of the benefits from these transformers, from these neural methods, in terms of ranking quality. So I'll show results later, where we'll see these models perform very well, much better than something like BM25. They're roughly comparable to dense retrieval models. But we have these different properties, sparse representations that we can look at, we can inspect, we can refine in different ways. To give another example of that, here we have a document that's an image. We again have a sparse encoder, and we can encode that image into a sparse vector as well, which we then can compare with that query representation. So like these LLM pipelines I showed, that because they output language can be put together in different ways, as long as we have types of encoders that all map to some English vocabulary, create these sparse representations grounded in English with the similar vocabulary, we have compatible sparse representations that we get out. So for example, maybe the sparse encoder for the image had never seen the sparse encoder for the document. They were trained entirely separately. Maybe they were not even trained together. They were trained using some loss that did not require the two encoders to be used together. Yet both of them produce this natural language sparse representation. The way scoring works here, if it's not totally clear, we just compute the dot product between the sparse representations in order to get a similarity score between that query and that document. So for example, we see that UMass is 1.6 and from the image representation, it's 1.9 for the query representation. Multiply those together, sum with the product of the two Amherst weights, and so on. The point being, this type of scoring is well suited to an inverted index. I won't show the slides today, but we can essentially rewrite something like TF-IDF, call it a sparse encoder, show how it outputs a sparse vector of this type, and then essentially an inverted index is an efficient way to compute similarities between sparse vectors. Because of course, in an inverted index, we're simply keeping a list of the documents that contain each term, and then we iterate over the query terms and can store the documents like so. There are a lot of scenarios this can actually be used in. I showed an example just now of a multimodal encoder. There are also papers doing this multilingually. Something I'll talk about later today is using this to enrich representations with entities. So here we see the same query, UMass Amherst, in quotes, a normal sparse encoder, meaning some normal textual vocabulary. We could have a separate entity-aware sparse encoder that produces terms like UMass Amherst, the Wikipedia page, and Amherst, Massachusetts, the Wikipedia page. I'll talk about how this is done in a later part of the talk. And then given these two representations, we can combine them into some final representation of that input. This could be done in a single model where we extend the vocabulary. It can be done with separate models where we merge them into the final representation. It doesn't really matter. And so this allows us to create these grounded representations of queries and documents, grounded in language, that are very flexible in the sense that we can mix and match these encoders, or we can compare to different modalities as long as we have a modality for that encoder. And one nice property when developing these things is that you can look at the representation and see the degree to which it makes sense. If you have a sparse representation that isn't so sparse, things are not working, essentially. So to sum up interesting parts of learned sparse retrieval before I get into a little bit of background, if you look at generalization benchmarks like BEER, in-domain benchmarks like Trek Deep Learning or MS Marco, they're effective in both places. The general story here is they're comparable to dense retrieval methods, maybe slightly worse. It's not totally clear because, of course, there's been a lot more research on dense retrieval, and the best leaderboard numbers from dense retrieval methods are combining all sorts of things. Maybe you have a 4-stage pipeline like Dragon with different types of losses and so on. Learned sparse retrieval is relatively underexplored, and so we don't see the same degree of combining teacher models and so on. But if we compare apples to apples, they're very comparable. Learned sparse retrieval is very, very slightly worse in terms of metrics like NDCG, if at all. It really depends on what you look at. They're very efficient. So as I showed you, we can put this in an inverted index like Apache Solr. They have strange weight properties because these weights are coming from a transformer. They don't follow the same distribution weights we're familiar with, like from TF-IDF. There was recent work at CIIR doing approximate retrieval over learned sparse representations. They got the retrieval speed down to 300 microseconds on MS Marco, so less than 1 millisecond. Of course, this depends on your document collection and tuning the parameters of that index and so on, but they can be extremely efficient. That's not a concern. And as I've been hitting on, one property I really like from them is that they're so flexible. So we could have something like an image, we could have something like a query, a tweet, And we can put it all in the same type of representation, compare the representations, refine them, use large language models to suggest what should go in them, as we'll see with entities, where one approach we use is essentially entity retrieval from an LLM to create the representation at query time, and so on. And of course, this is possible because the representations are transparent. In the same way an LLM output is transparent, a sparse representation, English terms attached to weights is transparent. So that's my intro to learn sparse retrieval, my pitch for why I think this is interesting, the flexibility I've been talking about. I want to step back for a second and talk about, basically put these methods in context. So I'll really briefly describe my view of dense retrieval methods and generative retrieval methods, so we're on the same footing and we can compare them. And then we'll start talking about properties of learned sparse retrieval methods, whether they're really grounded, as I say, how we can enrich those representations with entities, how we can create multimodal representations, and then I'll conclude. So I'm sure everyone is familiar with dense retrieval. Here we have some transformer encoder. We take some input text, maybe it's a query, maybe it's a document. We get these vectors out that you see on the left side of the blue boxes. These are latent representations. You see an example dense representation at the top right. Remember that dense here simply means that we expect the values to be most if not all the values to be non-zero. We can put these dense representations in approximate nearest neighbor index. In Silicon Valley, they like calling this a vector database. And then we can quickly find the nearest neighbors of that query representation. As with the sparse representation, the similarity computation is usually a dot product between the vectors or a cosine similarity between them. Generative retrieval is a recent approach. Too much happening to sum it up in the slide today, but just to give you an idea, here we're essentially moving those document representations inside the model. So if we have one representation per document, this looks a lot like dense retrieval, where we're now putting the representations in some model embedding layer instead. But there's, of course, other work that does multi-token representations that uses a mix of these latent representations and tokens and so on. But the point here is that the document IDs are being placed in the transformer's embedding layers. And so we give the transformer, the large language model, a query, and then it uses those embedding layers to generate the IDs of relevant documents. But as I said, the subject of the talk today is learned sparse retrieval, specifically in these different challenging settings and how we can refine representations. So I'll again show you an example of that. So we have the text as input to our transformer encoder at the bottom. We get out a contextualized embedding for every term. I'll describe different ways these encoders could work later. We're going to leave it as mostly a black box for now. And we get out the term importance weights, which can then go into this sparse representation. And as I said, we can use an inverted index for this. One way to think of an inverted index is a data structure that can quickly compute the dot product between two sparse vectors. Today,
So,
yep.
for the interrupt. So there is a question in the chat. How to decide on what these dimensions would be, or these are all terms in the vocabulary?
Yeah, so these are all terms in some vocabulary. I'll talk about how we can have a dynamic vocabulary or how we can expand our vocabulary in about 2 sections of the talk. But in a few slides, I'll explain, we're going to repurpose the masked language modeling machinery from BERT in order to produce these often. And so this is essentially, you have some set vocabulary, you have some representations of vocabulary terms, and you're determining which of those vocabulary terms should appear in the representation. So I guess the short answer is that this is fixed. That's a good segue to the point I was about to make here, which is what I will talk about today are these grounded representations. So where the dimensions in a vector correspond to terms in a vocabulary, but these can also be latent. So Hamed has a paper from 2018 with a pre-transformer architecture creating these types of representations. There's a recent one called Kale that was an ICTIR. There's no hard requirement that these sparse vectors be grounded in a vocabulary, but I think that if we do so, we gain a lot of nice properties. And so it's a setting that is worth thinking about. So now I'll talk about how these representations are produced, and that will answer this question in a little bit more detail of exactly how the vocabulary is used to produce them. So there are really three main components we need. We need some sparse encoder that takes text as input and then produces a sparse representation. We probably have some sort of a sparse regularization in order to minimize the number of non-zero dimensions in that vector. So, if we have a vocabulary of size 10,000, we don't want, 9,900 non-zero dimensions. This means the dimensions either contain very small values that aren't needed, or they're not actually grounded in language. In this talk, with this view of learned sparse retrieval, we don't want that. And then we need some supervision signal for training these. So these are a type of neural model like dense retrieval. The supervision signal we use is a loss very similar to in the dense setting, really the same. So I'm not going to talk about that today, but you can imagine, some sort of contrastive loss or pairwise loss where you have a query positive document pair and you're trying to rank that above the query and negative document pair. The regularization, I'm also not going to talk about much. This is just, use L1 regularization, L2, maybe you do post-processing to only keep the top K weights. Anything like that will work. There's not a lot, I think, that can be said there. What I want to focus on in this section is the sparse encoder, so how we actually produce these sparse representations. So the simplest thing we can possibly do is almost nothing. We call this a binary encoder. So if we have some text like Notre Dame fire, we can tokenize that text. And then in the sparse representation, we can say the dimension is 1 if that term appeared in our input text and it's 0 otherwise. So you see that Notre Dame and fire are 1. Everything else in this vocabulary is 0. Let's say we're using a word piece vocabulary, like a BERT vocabulary. This is very common. In that case, we have about 32,000 vocabulary terms. This obviously is not going to work very well. We are not actually learning anything. We're not learning weights of terms. We're not learning to expand of the vocabulary. So on its own, of course, this is not what we want to do. We can go a little bit further by weighting those dimensions. So here we're adding an MLP after the transformer and an MLP afterwards. So that transformer computes the contextualized embedding of each of these input terms, so Notre Dame and fire. And then this MLP predicts a term weight for each of those terms. So unicoil, for example, is a method that works like this. I should mention the paper at the top of the screen, the citation, is a reproducibility paper / survey looking at a lot of different learned sparse retrieval methods, coming up with a common way to describe them, training them in a common framework, and then analyzing their different properties. So we call this an MLP encoder, meaning we use an MLP to produce a weight for every term in the input text. So now we do weighting, but we can't do any expansion. The only non-zero elements in our vector are those that were also in the input text. So here, Notre Dame and fire. What we really want to do is some combination of both expansion and weighting. So here you see again the transformer taking those tokens as input. And now, as I hinted at earlier, we're using this masked language modeling head in order to essentially predict logits over the full vocabulary. And then we'll do some aggregation of these logits. So for example, you see the first term in that sparse representation is France. It has a weight 0.3. The way that weight is obtained is by looking at each of these input terms and seeing what weight the language modeling head produces for the term France. Maybe the first term is 0, so CLS produces 0, maybe the second term Notre produces 0.3, maybe the third produces 0.1, and so on, and then max aggregating over these. So we're essentially making the statement that the weight of fire in that output representation of France in that output representation is the maximum weight of France from any of the terms in the input. This is closely related to the popular Splade model. Sean McAvaney's EPIC model also had something like this on the document encoding side. The point here is that we're repurposing that language modeling head, which predicts what goes in a masked position in order to predict what terms should go in that sparse representation. So by doing this, we both get weighting, like with the MLP approach, but we also get expansion of the vocabulary. So now we can have richer representations that, of course, have a better chance of matching the query. I should mention that we can use these encoders on the query and or the document side, and we can mix and match them. So in a little bit, I'll show, for example, maybe a binary query encoder. So there's no processing done at query time, and the documents are represented using the MLM encoder. And in this sort of setting, we hope that the expansion the MLM encoder does is sufficient to find whatever terms would be in a related query, such that we're okay with just that binary representation of the query itself. Before I get into those results, though, I want to step back and point out that what is being done here with that masked language modeling encoder is really similar to several other things that we're probably familiar with to different degrees. So I mentioned dense retrieval earlier. Here, as I said, we have some transformer, we have some input to the transformer, and we produce a dense vector, an embedding of that input. So here I show the query going into transformer, a query embedding coming out, and then we compute the scores between different documents by taking the dot product between that query dense vector and these document dense vectors that we've already pre-computed at indexing time. So that's dense retrieval. Masked language modeling is really, really similar in some senses. What we're doing here is something like dense retrieval over a fixed vocabulary. So as before, we're inserting some text into a transformer. By convention with masked language modeling, the pre-training task, one or more parts of the input is masked out, and then we predict what would have gone there. When we use this to learn sparse representations, we don't actually mask anything. We apply the masked language modeling head to all the positions. But here I'm talking about the pre-training task specifically. So we have these tokens, like bank makes masked. This is probably something like loans. It's not bank in the sense of next to a river if we're talking about makes. So loans would be a better guess here than river. We get a dense vector out for that masked term. And then we're comparing that dense vector for the masked term to all the terms we know about. So we're saying, loans has a score of 3, river has a score of 0.1, something else has another score, and et cetera. So I think it's a useful, conceptual connection to make when thinking about these things, that we're doing something really close to dense retrieval. It's just that what we're retrieving are different terms. And when we say that, we retrieve term loans with score 3, that, goes into the sparse representation. We look at the dimension that corresponds to loans in our vocabulary, and we say it has weight 3. This is also extremely close to LLM generation. So here we again have bank makes, and rather than a mask token, I'm simply stopping because we want to generate the next term. Here we call it a language modeling head rather than a masked language modeling head, but it's very, very close, if not exactly the same, depending on the architectures you're looking at. So we have this language modeling head. It takes the third vector, the next token, as input. It just does some simple transformations. There's like a projection and a layer norm and a ReLU activation. Nothing, that changes this conceptual understanding of what's going on. We get that dense vector out. And then again, we essentially do retrieval over the LLM's vocabulary to decide what the next term is. So we essentially have a ranking of terms. If you're doing, beam search with a beam size of 3, this means you're going to look at the top 3 ranked terms and, explore those beams. Maybe there's another setting where you sample. Maybe there's another setting where you always take the top ranked term. But these things are all, very closely related together. So you can almost think of learned sparse retrieval as retrieving the terms that are related to this input, and then using that retrieval or that ranking to create the sparse representation. But now, getting back to the properties of these models. So I promised at the beginning in my motivation that these are grounded in natural language. There's some meaning to the dimensions. I just made some explanation for why that's the case. We have this mass language modeling head, or with a decoder transformer, this language modeling head. But let's look at some results to see if we can shed some light on this one way or the other. So here we're using a query encoder that does both expansion and weighting. If you remember, I called this the MLM encoder. And we have a document with no weighting at all. So these are the results we get on several data sets. So MS Marco, Trek Deep Learning 19 and 20, and TripClick, which is a medical domain data set. These results are not great. They're, I think, around 10% lower than BM25 with no weighting. So something's happening. We haven't totally satisfied ourselves at this point because we expect the results to be much better. And in fact, if we enable weighting so that we aren't only using a binary encoder, we do see a pretty large improvement. However, if we swap the sides around, so now we're allowing the document side to do expansion and weighting. On the query side, we're doing no weighting at all. That means we only have a 0 or 1 to, indicating whether the term appeared. So this is telling us about grounding because there's no freedom to repurpose the terms. The document encoder can only match terms that should appear in the query. They have no, so to speak, opportunity to collaborate and say, let's repurpose the into a latent dimension and of into another latent dimension and so on, which is behavior we do see in some cases, like in the multimodal setting I'll briefly talk about. So again, here, the query has no weighting. This really can only work if the document terms have some meaning that corresponds to the query terms. There's no learning on the query side at all. There's no opportunity to, sneakily turn things into a latent representation. So what we see in this setting is things work really well. So they're now comparable to dense retrieval methods. It depends on exactly, of course, the setting you look at and so on, but they're very competitive, if not slightly better, depending on the setting. And so document expansion is, enough to do really well. If we enable weighting on the query side, we see a small improvement, not a huge improvement, but, clear gains, which is, I think, not so surprising. It's a little bit better if we can, estimate how important each term is in the query, rather than only saying the term is present or it's not. A nice property of using no weighting, of course, is that we don't even need a GPU at query time. All we're doing is tokenization. It's very simple. There's very little encoding there. We can also look at moving from weighting on the query side to both expansion and weighting on the query side. When we looked at the document earlier, we saw that it seems to be nice to have both expansion and weighting. For the sake of time, I'm not showing results comparing expansion only and weighting only and expansion plus weighting on the document side, but expansion is very helpful there. Strangely, at least when the documents, when the encoders are trained in domain, there's not a lot of improvement from turning weighting on the query side. It does seem to help when moving out of domain though, but I'm not going to get into those results today. So the takeaway here being that it does seem like our representations are grounded, and we can essentially use a GPU only at indexing time. We can get really far just by doing expansion and weighting of the documents without any sort of query processing that is using these GPU machinery. So now I want to talk a little bit about how we can take this further. So one unsatisfying part of what I've said so far is that, as a question pointed out, our vocabulary is, it's fixed. We have these 32,000 dimensions, and that's what we have to mess with. It's hard to imagine this can work well everywhere. And in fact, I'll show you an example where it should not work well. So say we have the query World War II causes. So we have WWI, because of the way word piece tokenization works, The second I becomes its own term in the vocabulary. So WWII is not a term, but WWI is. So this is quite weird. We've separated, the second I in World War II. This is an example Craig McDonald pointed out to me from Colbert. I think it's a nice one. And so if we have two documents, one talking about World War II and one talking about World War I, that happens to have, some other token that creates this I word piece, well, they both look equally relevant in terms of, a dot product. We can't keep the, both I's together in World War II. For me, at least, this is really strange, really unsatisfying. So we have World War I in both, but we have this issue with the second passage. And we see that when we use long documents and try to combine the representations of different passages in a document, we don't do so well as the document length increases. So here's summing the representations, taking the max, taking the max from each segment, taking the highest scoring passage is better. I don't want to go a lot into the details of these methods because for the sake of time. But the point being is, as we have a longer document and we're putting all these word pieces together from different parts of the document, we see a decrease as we include more and more passages. I think that's likely related to this tokenization issue. So what can we do about it? Well, we can ask whether we really want these word pieces in the first place. Maybe we want to get rid of them. I don't know. But what I'm going to think about here is extending them rather than replacing them. So if we have a query like, is US a member of the WHO or the World Health Organization? To a human reader, it's pretty clear that us, a member of WHO, doesn't make much sense, but United States, a member of the World Health Organization, does. So we have homonyms here. One way to handle that is by essentially refining or enriching this representation. So we add these entity tokens to it. So now it's a bit less ambiguous. We have World Health Organization, we have United States. Another issue that we see is this word piece issue. Maybe it's not obvious from looking at the learned sparse representation. We have word pieces like NTE, SHOT, CH, bio. This comes from the query BioNTech SHOT. And this is, again, an issue of collisions, like I showed you with World War II, where because we have this bag of words, sparse representation, it's not totally clear where each word piece came from. And as our input size increases more and more, we have the possibility of accidentally matching the query by taking different character engrams from different words in the document, which, of course, is not what we want. It's also very unsatisfying that we have a model that might be doing this. So how can we deal with it? One way, which we've seen in prior work, is essentially learn a different vocabulary. Maybe you do white space tokenization. So you define this new vocabulary, and then you do, you run this masked language modeling pre-training for more steps over this new vocabulary. So you can learn how to use it. And now at least you're not, splitting BioNTech into 3 terms. It's now essentially 1 token. That deals with collisions, but it doesn't deal with this issue of homonyms, because again, we don't know if US is us or United States, etc. So what we do in this work is we expand the vocabulary. We call it a dynamic vocabulary. So we essentially augment it with entities and concepts. So these are just Wikipedia pages. I think of a sparse representation, each dimension as pointing to something. So essentially what we're doing here is we're saying, in this representation, we can point to United States and say that's here with weight 3. We can point to World Health Organization and say that's here with weight 2.1, et cetera. So we have a richer representation because we're essentially expanding the vocabulary to include more tokens, and we're defining those tokens in a way that's useful to us and also grounded in some type of language. The way we do that is with 2 new ingredients. We have this candidate retrieval component that essentially looks at an input and says, returns things that might be relevant given that input. So you can imagine looking at this example of is US a member of WHO and outputting things like World Health Organization and global health, maybe something incorrect like the WHO, the band, et cetera. So it produces these candidates. And then we have a way to represent these candidates. We have some embeddings of them. Doesn't have to be trained alongside our BERT model. In fact, the examples I show you, none of them were trained alongside BERT. And we put these two ingredients together in order to decide which of these candidates should appear in the vocabulary and with what weight they should appear in the sparse representation when they should appear. So you see, for example, entity candidates like United States and World Health Organization, and these will be added to the representation with some weights. This could be part of an existing model. It could be like a second head in that model. So you have one head that produces a BERT vocabulary, another that produces entity candidates. There's no reason it has to be. It could be a separate model that maybe you run later or you update in some way that essentially annotates these documents with related entities and then adds them into the representation. So I'll talk about how well this performs, especially with respect to different ways to find candidates and to represent them. So we have some learned sparse retrieval model. This is a variant of EPIC or SPLAID, depending on how you look at it. It's a model that performs very well. I'm using only a word piece vocabulary. That's our base model we'll compare to. We add in some Wikipedia entities and concepts to that model using the steps I just showed you with candidate retrieval and the representations. We look at how they perform on some entity-rich data sets, meaning data sets where we see entities appearing quite a lot. We train on some synthetic queries. And then we look at different ways to find candidates, essentially, and different ways to embed those candidates. So first, I'll show you across 3 data sets, moving from the standard word piece vocabulary to this vocabulary that also incorporates entities. Here, we're only looking at linked entities, meaning entities or concepts that appear in the text itself, not that are related to the text necessarily. So a more strict sense than if we did entity retrieval. And then we use LAC embeddings of entity descriptions. This is a dense retrieval model targeted at entities. So you see we get a pretty consistent increase across these different data sets. We can do better as we improve the candidate retrieval step, this entity linking, and look at different types of embeddings. So here is linking from the past slide, rel. We can use VM25 just to retrieve entity descriptions. This works surprisingly well. It's only slightly worse than a rel on this data set codec. The trends I'm showing you are the same across all data sets. I'm picking codec specifically because we have some human selection of entities, so it's kind of interesting to compare to that one. If we do LLM generation, so basically taking the query, asking some LLM what entities are related to this query, and then using some entity embedding to add those to our vocabulary, we do even better. I forgot to mention on the document side, we're always doing entity linking. So this is always pretty fast, rel is something like 5 milliseconds per document on CPU. So this LLM generation is happening on the query side only. So we, again, have this flexibility where we're treating query and document differently, and we have a different encoding process. But we get a pretty big improvement from switching to mixtral there. GPT-4, unsurprisingly, is better than mixtral. And we can also look at entities selected by a human. This is slightly worse than GPT-4. If we look at why, it's not that surprising. So GPT-4 is good at finding entities that might just not come to mind. So if I look at the Siege of Savannah Wikipedia page, I see the French were involved in that. So it's related to this query about French support during the American Revolutionary War. I went through American history class. I didn't know that at the top of my head. Maybe it's only me, I don't know, but it's not surprising to see that GPT-4 is good at finding entities that are related that might not be the ones that immediately come to mind. Same thing with a query about NFTs. It finds terminology like digital art, digital asset. That makes sense when I see it, but it's not the first thing I would have thought of if I were to look for entities or concepts related to NFTs. Finally, we can look at some different ways to embed those entities. I showed you LAC before. This is just a dense retrieval model taking entity descriptions as input. We can also use the input tokens of our transformer model. So this means we're not adding any outside information. We're mostly just fixing that collision issue with tokenization. This performs okay, not as good as these lack embeddings of entity descriptions. We can embed the descriptions in a different way, works similarly. We can use Wikipedia to vec, which is essentially word to vec run over Wikipedia with entity Wikipedia page tokens, essentially. So this is pretty simple. There's no transformer involved in producing the representations, and it works quite well. The best by a little bit is Blink. So this is that Facebook entity retrieval method. So it's a dense encoder, and we encode the entity descriptions from Wikipedia in order to create the embeddings. So the point being here, we have lots of choices for how we create these embeddings. They all seem to work to some extent. In the short amount of time I have remaining, I'm briefly going to talk about moving all of this to a multimodal setting, which was something I wanted to explore because for a little while I wanted to see where these methods would fail. I assumed, it should be fairly easy to find some setting where they don't work well at all. Actually, we were finding ways to make them work in the settings we thought that were somewhat challenging. But I think multimodal is an interesting one because we have no text to begin with. It is a hard problem to ground the images because there's no text associated with them. So what we want, and actually an example from the method I'm going to talk about, is something like this, where we see an image on the left, and then we get some terms over the vocabulary and weights of what appears in that image. So you see things like animal with the highest weights, boy, buffalo, people walking, cow, etc. Don't ask me whether these are cows or buffaloes. I'll defer to someone who knows. But the point being, they're related animals here. We're not the first to do learn sparse retrieval in a multimodal setting, but we're the first to do it in a very lightweight way, I would say. So there's work, for example, LexLip, using a huge number of text image pairs, 13 million. There's other work using, hundreds or I think a billion with complicated architecture. So it can be done. But the insight or the approach we wanted to take here is to create them in a very lightweight way, essentially based on the idea that dense representation should already have everything we need to know about the image in them. And we just need to figure out how to take that dense representation of a caption or an image and convert it to a sparse vector. Thinking back to that MLM versus dense retrieval slide, hopefully you see the connection. With something like MLM, in that textual embedding, we have what we need to predict weights of a vocabulary. If this embedding, really represents an image well, we should also have what we need there in order to predict, weights over a vocabulary as well. The challenge we struggled with to make this work is an issue I hinted at earlier, where the terms just lose their meaning. So there's nothing really enforcing the fact that I don't know, boy in the vocabulary corresponds to boy in the image. If you have a huge vocabulary with lots of terms, lots of stop words, you can just end up with a model that essentially repurposes these dimensions in the sparse vector to create some sort of latent representation of the input. So here you see a model where training failed, and you get terms like accent, ship, crow from this image, which are just unrelated. The way we solve this is essentially limiting the freedom on our text encoder side. We have a schedule where we don't allow it to expand at the beginning of training, and then we slowly give it the ability to expand tokens. So to add terms that were not in the textual query, the document here is an image. The reason that helps is because if there's no expansion on the query side, then the image encoder needs to generate terms that correspond to actual terms in the query, and so they have to be related in some way, is the quick explanation. If we look at some of these image caption retrieval data sets, so this is MS Coco, similar results on other data sets like Flickr 30K. We have a textual query. The documents are images. If we compare to something like this Blimp DITS model, we see we're a little bit worse if we don't allow any sort of expansion in the query representation. So we're only doing weighting. But if we use this approach where we have a schedule and we slowly allow expansion during training, we can get really close to the performance we got with that dense model. So we're not outperforming it, but we're also using a distillation loss here, so I wouldn't expect to outperform it. The point here is that we're able to take this image and this image embedding that had a totally latent representation and fit it into our learn sparse retrieval framework and represent it in this way for retrieval. So that brings me to the end of my talk. I'm getting close to the end in terms of time anyway. So I've talked about learn sparse retrieval as a flexible, grounded representation for queries and documents. We've looked at these multimodal methods really, really briefly. I can, happy to discuss this more. I didn't spend a lot of time on it. We've also looked at these dynamic vocabularies, so how we can, improve the expressive power of these representations. And I think this is a really interesting way to do neural IR personally, because of just the flexibility it gives us, both in terms of understanding what's happening, debugging these models, but also just kind of imagination space, how we can combine things together, how we can, iterate on a representation, as opposed to, for example, having image dense retrieval, where both the text encoder and the image encoder have to be trained together. They have to, be creating latent representations that are in the same space, and so on. Because we're using language as the representation, we no longer have this problem of aligning things with a specific latent space. As long as we can produce a reasonable natural language description here over vocabulary, then we can do things fairly independently. So thanks a lot for listening. I'm happy to take any questions.
Thank you so much. Let's thank Andrew. Thanks for the very interesting talk. We have about 5 minutes for questions. Any question from the audience or folks online?
Hello, very great talk. So I want to ask if this sparse representation can handle the case where, like, for some certain query, you don't want some words to appear, like this kind of negation problem.
Yeah, that's something actually I've been thinking a lot about recently. So a technical detail I glossed over is there's typically a rel-u after this masked language modeling head, so anything negative becomes 0. There's no reason it has to be that way. So for example, we could see something like, I don't know, protein bar without nuts, and look at that nuts dimension in the vocabulary and set it to a negative value, saying, we don't want to find this this particular product, for whatever reason. So conceptually, I could imagine using the representation in that way, but I don't know if we're doing this. And of course, there are other ways that we could encode this, right? We could have, we could in some way recognize that without nuts is an important phrase or some sort of concept we want to encode here, and we could allocate a new vocabulary term to that, and represent that idea of no nuts, please, in that way. So I guess to answer your question, I can imagine ways to do it. I think this area is not that heavily explored, and I don't know of any work looking at that.
Thank you. I read one question from the chat. It says, coming back to the motivating example of transferring knowledge amongst models by grounding through language, are these vectors transferable across models?
Yeah, they are. So this Devo paper was the first opportunity I had to start making this argument. I have other work at different stages of publication, and you absolutely can mix and match models. So you can take a splayed V2 checkpoint, you can, and then use that for the query, and then, I don't know, use a Roberta checkpoint for the document. Roberta was pre-trained totally independently of BERT. They've never seen each other. As long as you make sure the vocabulary lines up, it absolutely can work.
Thank you. I'll also ask one question. I want to know what are your thoughts about dense retrieval now? So in what scenarios do you recommend using dense retrieval compared to the sparse retrieval, or vice versa?
Yeah, So dense retrieval is interesting in that we have these latent representations, and it kind of feels like we don't know what's in that representation. We must be able to put a lot in it. It must be a very, powerful, useful thing. In practice, so this is all part of my motivation. For example, looking at the multimodal work, I thought, maybe it doesn't work here. Maybe we can show this. This is the, the limit of a sparse representation. It's just too hard to ground the image, something like that. I don't have a good place to point to. So I can imagine, if you have a setting where, for whatever reason, it would be a lot of work to have the vocabulary terms you want. Hard to think of that off the top of my head. Or maybe it's just even this negation setting. Maybe dense retrieval could work better there. But I think what we're seeing is, growing number of examples where, despite these methods seeming kind of simple and the fact they're just these weighted bags of words, they work really well. Yeah.
One more question from the audience.
Thanks for the talk. In your experience, has there ever been, or do you think there'd be an issue where there's some concepts or something you want to represent that some sort of word or entity can't really properly convey?
Yeah, so we looked for this with like images. So things like textures, like maybe you have a roof with like a very certain pattern or like a look to it. Maybe there's some entity or concept that someone who's an expert on what roofs look like would know to say there. But something like this is hard for me to point to the specific vocabulary terms that should appear. I can imagine if you think of meta things about language, like, I don't know, like the tone of a document, you might want some different way to encode that. That's not necessarily an entity or a concept. Maybe something like an expertise level, you would need to have some new vocabulary terms. But these are all things that I can at least imagine a way that could be included in a vocabulary. It's hard to think of examples of something that I just cannot be represented here if we're willing to expand the vocabulary.
Okay, thank you. So we don't have time for any more questions. So let's thank the speaker for last time. Thanks again. We really enjoyed the talk, and see you in a couple minutes in the other Zoom link.
Sounds good. Thanks.
Thank you. Thank you all for joining.